Okay, so let's continue. If we use the assembled global K matrix, if we consider a partially assembled K matrix, and as long as the okay, so as long as the all the connected elements have already been assembled into the K matrix, then we can know the corresponding right hand side elements. They are the known external load. They are the known external loads. So it means that we have the static conditions. So we can eliminate the corresponding degrees of freedom by the static condensations. So if we solve a problems like this one, okay. So sometimes if we just assemble if we assemble the elements in the top layer of the structures, so it means we need to assemble these two beam elements, and also we need to assemble the three column elements, and the required degrees of freedom will be the okay. So we need to use the nodal degrees of freedom for these 6 nodal points. But after we assemble the 5 elements into the global K matrix, then which degrees of freedom we can eliminate? Okay. If it is in the classroom, I will ask one of you to answer the questions. But right now, you try to figure out it by yourself. If we assemble the 2 beam elements and the 3 column elements, then which degrees of freedom we can eliminate based on the static condensations? Okay, I will leave 1 minute to 2 minutes for you to think about the questions. How many nodal degrees of freedom we can eliminate based on the static condensation? Okay, the answer will be the okay. If we assemble the 5 elements in the top layer, then for the nodal point 1, 2, and 3, for these 3 nodal points, since all the connected elements have been assembled into the K matrix, so we can use the static condensation to eliminate the corresponding degrees of freedom. So if it is a plane frame problems, So we can eliminate 3 times 3. So there are 9 degrees of freedom can be eliminated from the global K matrix. Also remember, the eliminated degrees of freedom, it doesn't mean that we can just throw them away. Actually, they are still unknowns, and we need to solve the unknowns later. But it doesn't mean that we can forget them. We can forget about them and do not solve them. Okay, if we assemble the 5 elements connected to the top layer, then we can use the static condensations to eliminate the degrees of freedom related to the first layer. But for the node point 4, 5, and 6, we need to use them in the global K matrix, since we need to assemble the 3 column elements. So we need the nodal degrees of freedom for both node 1 and node 4, node 2 and node 5, node 3 and node 6. But we cannot use the static condensation to eliminate the degrees of freedom related to 5, 4, 5, and 6. Since, for example, for the node point 4, there are 3 elements connected to the element 4, but we assembled only one of these. Assembled only one of these 3 elements, so it is not complete. If we check the related the corresponding right hand side force vector, we don't know the member end force of this column element. Okay, so we can eliminate these 3. When we calculate the global K matrix, originally we need a K which is 18 by 18. Okay, since the right now we need to consider all the 6 nodal degrees of freedom, all the degrees of freedom for these 6 matrix, for these 6 nodal points. So we need a dimension of the 18 by 18 global stiffness matrix. But if we use the static condensations, this matrix can be changed to a for this assembled global K matrix, we can eliminate the degrees of freedom related to the node points 1, 2, and 3. So there are 9 degrees of freedom they can be eliminated. So the 18 by 18 matrix can be condensed to a 9 by 9 matrix. Okay, so it is a smaller dimensions. Okay, so that's the first step. We can assemble all elements related to the top layer, and then we can use the static condensations to condense out these 3. Okay, then we need to assemble the beams and the column for the next layer. Okay, so there are node points 8, 7, 8, and 9. Okay, so after the static condensations, right now the 9 by 9 matrix, which include the nodal degrees of freedom for the nodal points 4, 5, and 6. Then we need to assemble the 2 beam elements and the 3 column elements for the next layer. Okay. Then we need to expand the K matrix, since we need to include the nodal degrees of freedom for the 7, 8, and 9. So the matrix will become 18 by 18 again. Okay. So since right now we need to include the nodal degrees of freedom for the node point 7, 8, and 9. Okay, since in this case we can assemble the 3 column element stiffness matrix into the global stiffness matrix. So it will be a 18 by 18 matrix. After we assemble the 5 elements for the next layer into the global K, then you will find the 4, 5, and the 6 nodal degrees of freedom. They can be condensed out. So the K matrix will be changed to the 9 by 9 again. Okay, since we can eliminate the degrees of freedom related to the nodal points 4, 5, and 6. Okay, so again it will be changed to a 9 by 9 matrix. Then the next step, we will assemble the beams, the columns, okay. Now we need to change the dimensions to the 18 by 18 again. Since we need to add nodal points 10, 11, and 12, the 3 nodal degrees, the nodal degrees of freedom related to these 3 nodal points, we need to add them to the global K matrix. And right now, the nodal points 10, 11, and 12, they are the rigid supports. So we don't know, even we assembled all elements connected to the nodal points 10, 11, and 12, we don't know the corresponding right-hand side elements. Since the corresponding right-hand side elements, they are the reactions. The reactions, we don't know their values. But for the 7, 8, and 9 nodal points, they are, after we assemble the 5 elements into the global K, then we can know their values. So we can use the static condensation to eliminate these 3. And or you can say, then we can solve the unknowns. After we solve the unknowns, we will take the step backward, step by step, to solve the eliminated degrees of freedom. Okay, so that's the one of the technique we can use for the static condensations. Okay, the other applications, I will draw structures. Okay, if we got a structure like this one, and how can we solve the problem? So we can see there are three parts of the structures. For each part of the structures, it includes several elements. And for these problems, first we can assume it is let's say it is a basic unit sometimes it is called a super element. Okay, so that's the parts of the super elements. If we use the plane truss element, it includes four nodal points and the five elements. And the five elements. And when we derive the stimulus matrix for this super element, we will assume there is no member loadings applied to this unit. If you got the member loadings for these structures, then you can use the principle of superpositions. You can solve the structures after we added the virtual supports to these two ends, and then you can solve that. Okay, so for these structures, we need four joints and five elements. And the five elements, they are the plane truss elements. They are the plane truss elements. So for the plane truss elements, you need a 4x4 element stiffness matrix. And okay, so we can calculate the part of the K matrix, which include all the five joints. What will be the dimensions of the partially assembled K matrix for this unit? Since we got four nodal points, so the dimensions of this matrix will be an 8x8, which includes the U1, V1 until the U4, V4. Okay, and the 8x8 matrix, which is assembled by five element stiffness matrix for these five elements. So we need to calculate the five elements, and right now we can use and that's a coordinate system used only for this unit, and also we have the elements coordinate system, which is defined by the from the node A to the node B, and you can say they are the X double prime, the Y double prime. Okay, so we can assemble the K matrix for this unit. It is a 8x8 matrix, and for this matrix, we since we assume there is no member loading, so it means that we do not have the external loads applied to the node point 2 and the node point 3. Okay, since we will treat this unit as an element, and which is a similar element like the truss element or beam or the frame element. So when we derive the element stiffness matrix, we will assume there is no member loadings. So between these two end joints, no external loads will be applied to the between these two endpoints. So there is no it is an assumption. There is no external loads applied to this part. So we know the force they should be equal to 0. Okay, so we know the px2, py2, px3, py3, the external loads, they are equal to zeros. So they are the static conditions. They are the static conditions. So we can use the static condensations. Okay. So since we know the corresponding elements in the force vectors, they are equal to zeros. They are equal to zeros. So we can apply the static condensations to eliminate the corresponding degrees of freedom. So it will be these 4 degrees of freedom, they can be eliminated. So we will do the static condensations. After we do the static condensation, the 8x8 matrix can change it to a 4x4 matrix, and which include U1, V1, U4, V4, and the end force, and the end force. It is a partially assembled matrix, and then we use the static condensations to get the results of the 4x4 matrix. Okay, so that's the method we can use. Another similar problems. If we consider a frame problems, but the frame problems, we need to consider the variable cross sections. For this beam element, we have the variable cross sections. Okay, it is not a uniform cross section, so the I and the A, the moment of inertia and the cross sectional area, they are not constant. And for different cross sections, we have different I and A values. And also, if you consider the shear deformation, the shear area will also be changed. Okay, how can we treat an element like this one? You can use the static condensations. So you can add some internal nodal points. For example, they are the A1, A2, A3 until the AM. Okay, so we can add some internal nodal points, and that's the center line of the beam. Then from A to A1, treat it as a constant I and A element. Okay, since we have already derived the element stiffness matrix for the constant I and for the constant A, or the constant AS. So we can use the Actually, it is only an assumption, since for the real problems, it could be a continuously changed I and A. But if we cut the entire element into many small elements, then even we use the constant I and the constant A to consider for a very small part of the element, I think the errors will not be too much. So you can say that it is an approximate solutions, but it is an acceptable approximate solution. So for from the node point A to the node point A1, which is 6 by 6. Also from A1 to A2, we treat the K from the A1 to the point A2. It is another constant I and A elements, but the constant I and A, they will be different from the first element, since it is an approximate solutions for the continuously varied elements. Okay, so we can continue to the next. And then we can, for example, if we cut it into 10, if 10 small sections used, then we need to assemble a K matrix, which include for 10 small sections, we need 11 nodal points. And if it is a frame problems, we need 3 degrees of freedom for each nodal point. So the K matrix will be a 33 by 33. It is a 33 by 1. It is a 33 by 1. Okay. So since if we cut it into 10 small segments, then also we need 2 endpoints for each small element. And so totally 10 segments, we need 11 nodal points. And only the 2 endpoints, they are the node points considered by the sometimes that's the program user, he needs to know. But the inside node usually considered only by the programmer. Okay, so after we assemble the K matrix, which include a 33 by 33 matrix, the 33 by 1 displacement vector, the 33 by 1 for the force vector. Remember, when we derive the element stiffness matrix, we neglect any member loadings. So we do not have any external loads applied to the internal 9 nodal points. So for all these 9 internal nodal points, the applied loadings, they are equal to zeros. They are equal to zeros. So the totally here will be the 9 times 3. Totally it will be 27 degrees of freedom. The 27 degrees of freedom, we know the applied loadings, they are equal to zeros. So they are the static conditions. So they are the static conditions. So we know all the 9 internal nodal points, the corresponding applied loadings, they are equal to zeros. So right now we will use the static condensations to condense out the 27 degrees of freedom. So we will use the static condensations. Okay, then this 33 by 33 matrix, will be changed to a 6 by 6. And the remainder degrees of freedom will be only the node point A and the node point B. And all the internal node points will be eliminated. But after we solve the A and the B, the nodal displacements, then we need to go back to the original 27 equations, and we need to use those eliminated equations. The total number of the eliminated equations will be 27 equations. After we solve the nodal displacements for node point A and the node point B, at the first stage, only these two will be solved. After we solve these 6 degrees of freedom, then we need to solve the 27 degrees of freedom inside this element. Okay, so then we can output the results. Okay, it is another applications for the static condensations. Okay, I think it will be the end of today's course. If you got any questions, I think you can leave a message in the Moodle. Although I didn't read the Moodle very often, but since we cannot see each other in the classroom, so I will read it more often and try to answer your questions. Okay.